Let me now present to you version number 3. You can see this is one example of massaging the loop counters. You may not actually apply this directly to your application, but at least you know you should really be creative about setting and updating the loop counters. Let's now see the final third version, and let's also consider two cases when there are no duplicates versus when there are duplicates. So now the thing we have changed was this. So we still got these Boolean variable as the exit condition as part of the state condition. And now the important thing for you to know is this. We still got I is initialized to be 0. However, for j, we say that j is initialized to be I plus 1. So what does that mean? That means when I is equal to 0, in that case, right? So j will be initialized to be I plus 1, which will be 1 over here. And then notice that the array we're considering is a different array. So the maximum index will be 3. So that's why we got 1, 2, and also 3. And then when we actually finish all the iteration for the inner loop over here, we'll actually go back to the outer loop. So I will be incremented to 1. And then you can see when I is equal to 1, what will be the initial value for j? It should be I plus 1. I plus 1 will be 1 plus 1, 2. And all the way to the maximum index 3. And then when we finish terminate the inner loop, when we go back to the outer loop, I will be incremented from 1 to 2 over here. And then what will be I plus 1? 2 plus 1 will be 3. And 3 is already the maximum index, meaning that we only do one iteration. It's quite clever solution over here. You can see the pattern right now, we don't have the 9 anymore, right? In some way, it's more like a, if you think about it, so it used to be, you can think about if the length of the array is simply just n, right? You can think about for version 1 and also version 2. What we got is, we got 0, let's say for I and j. Let me just be a little bit more explicit over here. Let's talk about I and j over here. Okay, for version 1 and version 2. When I is equal to 0, j is going to be from 1 all the way to n minus 1. And when I is equal to 1, j is also going to be 0 all the way to n minus 1, right? Now you can see the size of this particular range over here is actually n. And the size for this particular range is also n, right? And you're going to repeat this pattern here for when I is from 0 all the way to n minus 1, right? So eventually, you're going to get n multiplied by n possible combinations for I and j. But what if we actually got this new version number 3, right? Let me just draw that very quickly to contrast to get it for you. So now when we got version number 3, okay, so for version number 3, let me put it here. Version number 3, and also we got I and j. When I is equal to 0, j is going to be, again, we're assuming that the length of the array is n. J is going to be I plus 1. So it's going to be 1 all the way from 1 to n minus 1, right? And then we go to the next iteration for the outer loop. And I may be 1. So that means j will be 2 to n minus 1, right? So now if you look at this size of the range over here. So for this one here, so size for the range will be n minus 1. And also this one here will be n minus 2, right? And then, so what's going to happen is, if you continue with the pattern over here, so all the way to when I is equal to maybe n minus 1, right? So what's going to happen is you're going to have the following sequence over here. Oh, by the way, when I is n minus 1, j will just be n, which is not going to be used at all. Okay, but just roughly speaking, what's going to happen is we're going to have the following sequence: n minus 1 plus, and also n minus 2, plus all the way to where you have only one valid value. Okay, for example, like pretty much like this case over here, when I is equal to the length of the array minus 1, in that case, j will just be the final value you can have, right? So just one valid value. You wouldn't have to go any further because you already violates the state condition over here. All right, so this one here, we don't have to really work out the math over here. It's not really necessary, but for those of you who are interested, you can feel free to see what this will end up being. Okay, but at least if you really compare the exact value of the number of iterations, this one over here, if you talk about this version number 3, You can think about like a version number 3. And this over here is version number 1 and 2, right? And you can see that this one here is strictly less than this particular number over here. However, we said asymptotically they are really the same. But I wouldn't get there too much, because that's something you will see in EECS1022 when you learn about the asymptotic analysis. But for now, just to get some insight into the pattern over here. All right, let's see this. One more thing to say. If you look at this pattern over here, you can see once we get 0, 1, do we still have to check 1, 0? No, because 1 here, the definition here say it's going to be I plus 1. So it's going to be starting from 2. So we get away from 1, 0, checking again. And also, we don't really check 0, 0 again, because again, we don't really check I and J being the same index, because J here will be strictly larger than I, which would be I plus 1, right? So you can see this one here. Let me just say this part of the code over here is really meant to make the improvement over here. So it really got rid of, okay, number 1, like a 0, 0, right? You know what I meant. So I and J being 0 and 0, for example. And also number 2, also after you have checked 0, 1, you actually don't check 1, 0 anymore. Okay, so just to remind you over here. All right, final case to consider, which will be case number 2 for version number 3. What if there were duplicates? Are we able to early exit? The answer is yes. Okay, you can see here we still got 0, 1, 2, 3, and also 1 and then 2, 3, right? The same loop counter pattern as before, which I already explained. And then, so now the only thing to see is why this will be the ultimate version. You can see here, as soon as we get to actually 1, 3 over here, you can see 1, 3 is 2 and 2. So this will be our first satisfaction witness that we see. So we can conclude right away the array actually got duplicates. In that case, we're going to set the has duplicate to be true. So that means not has duplicates and also not has duplicate are both of them are going to be both of them will be evaluated to simply just false. And then we're going to exit from the loop. Exit from both loops, because we have found the witness, the satisfaction witness. And you can see here, the final version here. You can see. Let me summarize, and then we are done. We don't have anything like a 0, 0. We don't have anything like having checked 0, 1. We're still checking 1, 0. We don't have them. We don't have that redundancy, and we also got early exit over here, meaning that as soon as we have found the satisfaction witness for the property we are checking, and we don't really got any more execution anymore, right? We just exit. So this will be the ultimate solution. But in reality, I would say all the 3 versions actually work. And it's really a matter of which one that you feel more comfortable about at this level. But you should really aim for as efficient implementation as possible. So maybe just try to really appreciate, just by adjusting this part of the loop counter over here, we are able to really avoid the duplicates that we have spoken about. And that's really something you can try to be creative about when you program your algorithm for later problems. And also, don't forget our principle about how to extend the state condition in the loop to really make sure as soon as you found the property, you're able to exit from the loop. And the same principle also applies to checking universal property, which you should also review as well. All right, so that's about our discussion for this example for nested loop. Hopefully that helps. And then from next video, we'll start talking about two-dimensional arrays.